jointly. We're sitting in the same room right now, which could be very interesting. But normally we will be teaching from different. Next week I'm going to be out in California, so I'll be teaching it from there, and he'll be from Chicago. So the subject here is machine learning, and we of course uploaded the slides to the platform. So hopefully you've downloaded it. I also uploaded a notebook, and it's on notebook. So if you don't know how to use Python Notebook, the books I would suggest that you learn this. I mean, I think most of you are probably taking VJ's course in Python, so you should hopefully know how to use Python notebooks. If you don't, then you should download the Anaconda Python distribution, which has the Python notebook in as part of that distribution, and that's sort of what we'll be using, at least for my part. Adam will be using R. So if you don't know R, you can submit either in R or in Python. If you don't know Python, you can submit in R. If you don't know R, you can submit in Python. So both languages, I think, are important to know if you're going to be a data scientist. So I'm going to start with something pretty simple.
Just 1 second.
Yeah.
If you don't know how to install R or RStudio, actually, there's an ACADS lecture where I talk about that, an introductory lecture on stats and data manipulation. So that's on YouTube even.
Mm-hmm. YouTube, wow. Mm-hmm.
Okay, I'll share the link, Adam, the YouTube link of that lecture.
It's the introductory one.
Yeah. Okay. Well, we'll get started. So the first slides here are just some introductory remarks about the course and how we're going to be teaching. So we're going to be attempting to equip you with some tools so you can use machine learning when you actually are in a situation where you have a practical problem with data, and you have some data you want to analyze or whatever to use some of those tools in your actual work. And of course, we can only in a 10-week course, which we are going to try to keep on a level that does not use a lot of heavy math. We can't do math, that's for sure. But we hope that we can inspire you to be more, because there's an enormous amount of material in machine learning, and it's a field that's developing incredibly fast. I mean, there are new things coming out almost every single day. So it's really active field. There are a lot of people doing research and a lot of stuff to learn in there. So we can inspire you to go further, either on or in some future courses. So as you can see, we'll be teaching this course, both of us in a sort of a tag team thing. But normally that tag team means that I'm going to be doing the first 45 minutes and Adam's going to do the second. So it's not really that tag team. But we will actually discuss and ask questions of each other, and of course we also encourage you to ask questions and take part in the discussion. So we'll try to make it as interactive as we can, and it starts with the tools being interactive. And as I pointed out before, we use different tools. I use Python, and Adam is expert in R. So that's a point of various contention, but hopefully we'll try to keep our tempers in check.
Between us, you'll learn Python.
Python. Yeah, well, we are both, so both of us are mathematicians. We both have PhDs in mathematics. And so for us, it's not, machine learning is not just learning a lot of formulas and some code. It's to understand what's going on. And a lot of times you find that the things don't work so well. So it's important to try to understand what goes on behind the formulas, so one can see how to fix things if they don't work out. That happens a lot.
And if I tag in for a second, the is if you just learn the thing as a recipe, like how to use something without any understanding, even if you graduate with the top marks in the world, 2 years from now you're going to be obsolete, because anything that you can learn by a recipe, guess what? This is machine learning. A machine can learn by recipe too, and it'll just be faster than you and cheaper than you. So it's really important, you know, even you don't have to understand the mathematical proofs of things, understand all the complicated algebra and how something comes about, like gradient descent. But if you don't have some idea of what's going on, you'll be mired in one spot. And so that, I agree with Niels most strongly that we're going to work very hard to try and give you an idea of what's going on, so you'll be able to not just do what we show you, but go beyond it. Right.
And we'll actually show you some examples that actually we discovered while we were preparing the course. We found some things that we hadn't thought about, but it prompted us to really think about these things. So we'll share those things with you. So what we agree on, maybe the only thing we agree on, is that machine learning is prediction. It's about making predictions. It's not about a lot of other things that people have been doing in data science through the years. Machine learning is about how to predict things. It's about making a machine learn enough that it can make some reasonable decision about what's going to happen, different data. So I mentioned that other fields, I'm particularly thinking of econometrics. People in economics and econometrics are more interested in understanding relationships, like causal relationships between various factors and data in the data set, and they're not so interested in predicting what happens. They get some data in, but machine learning is absolutely all about see what happens when you get new data and try to predict what happens from when you get new data. So this is machine learning is about using computers and training computers on existing data to make predictions when you get new data. And that's something that we hope to really emphasize in the course. It's not econometrics. It's not economics. It's really it's
not
really,
descriptive.
Yeah, not descriptive. It's predictive. So we'll start very simply and look at the model which is known as linear regression, and I think most of you have at least some idea of what this is. And so let's look at some data points here. So I have generated some data points here in the planes. We have a two-dimensional plane here, and we have points here. And the object of linear regression is to try to sort of find a line that best goes through these points. So here are some lines on 2 points, and we can see that we would probably agree that the yellow line is the one that, in some sense, fits these points the best. The red and the green line, well, I don't know, maybe it doesn't seem to fit so well. But of course, we have to really define what it means for a line to fit these points. Of course, we can't, the way these points are, we can't draw a line that goes through all the points. That's not possible. They're not linear. So let's how we actually define what means to what the best fitting line, what that means. So in order to do that, we need to do some math here. So a line is given by an equation here of this form here. It's that the coordinate can be expressed as a number a plus b times the x coordinate. So a is called the intercept, and b is called the slope of the line. So the line consists of all points of this form x, y, where x and y has this relationship here. So x here and y here.
I'd like to point out that I agree with him completely on this.
That's surprising.
Can I say?
Wow. Yeah. Well, that's the equation for a line in the plane. So we're trying to find a line, i.e., an equation of this form that fits the data best. So the points that we have in the plane, we're trying to a line that somehow find an A and a B that somehow fits this these points best possible. So let's see what does it mean. Let's define what it means to fit or to go through these points as much as possible. So you see this thing I've drawn here. Here the purple thing is a line, and then I have these data points here spread all over the plane. And so I want to measure how far is the data point here. So this is the one with a red circle around. This is one of my data points. How far is that from lying on the line? Well, my data point has an x-coordinate that's down here and a y-coordinate, which is here. My line, well, also this form a y equal to a plus bx. So if I take the x-coordinate, then there is a corresponding point on the line here whose y-coordinate is given by this. And so I can simply measure what is the distance from the data point here to the point on the line. And I measure it by looking at the difference between the two y-coordinates. Here I had the y-coordinate of the point on the corresponding point on the line. So it's a point that has the same x-coordinate as the data point here. Here's my data point. Here's its x-coordinate. Here is the point on the line corresponding to that x-coordinate. And so I can measure how far away I am from the point on the line by looking at this distance here between the y values. So I can do this for each of these points, these data points, and I can sum up all these differences. It's going to give me a measure of how far these points are from on the line. You see, if I have a data point that is on the line here, I am lucky enough data point that does lie on the line, then this distance is 0. So the error or the difference between the point and the point line is 0. So for all the points, all the data points on the line, this error term is 0. So I could use this to define what it means, or to define sort of what the error is between the data point and the line. And do this for every data point. I could compute this. I could then sum them all up. Now, normally you like to take the average, so you take the sum of these and then divide that by the number of data points. So this is one way to measure how far away we are from lying on the line. So you see, the smaller this number is, the better, the closer the data points are to actually lying on the line. So this is one can use this. I take here the absolute value. So that's the absolute value of this difference is actually the distance between the y-coordinate. Now it's very convenient, instead of using this measure, to take the square of this difference. So if you take the square of this difference, of course, I get something that's always positive, then equal to 0 anyway. And so I can take these squares, one for each data point, and I can sum them up and divide by the number of data points. And that gives me a number. Every time I take a line, draw a line, I can make this, for each data point here, I can compute this difference here and take the average. So every time I have a line as expressed by these two numbers, a and b, the intercept and the slope, I can construct this, or I can construct this number here, which depends on the line. It depends on these two numbers, a and b.
Okay, that's a question.
Sure.
Why did you call it L? Okay. It's a loss function.
Yes, that's right.
Tells
So
you how much you lose by S. I got it.
This is machine learning. This is what we would call the loss function. And so what's the idea here? The idea is that we want to find A and B. We want to find a line. So that means we want to find A and B. We want to find a line, A and B, that minimizes this number here. So you want to find A and B so that this number here is as small as possible. It can't be 0 because there is no line that goes through all of them. If this number here is 0, well, then because you are summing up positive numbers, a sum of positive numbers can only be 0 if they're all equal to 0. And that would mean that that all the data points lie on the line. And of course, see, that's not possible. So we can't get it to be 0, but we can try to find A and B so it's as small as possible. So that's the object here of this linear regression model here. We'd want to find A and B such that this loss function is minimal. So how do we find a function? Well, we take derivatives, put them equal to 0, and then we try to solve for the minimum. Now this is depending on what kind of function we have. This is not always possible to do that. We can have some highly nonlinear functions that we can't really solve, but there are other methods to do that, to use approximate method. In this case here, I should say that it is in fact possible to solve these equations here. But let's introduce this method, which is known as gradient descent method. So this is an iterative method that gives us an approximate solution to this problem. We're trying to find A and B that minimizes the loss function L. And so we can find a sequence of numbers that approximates this minimum, this A comma B, arbitrarily well. So how do we do this? We have to take the gradient of this loss function. The gradient, well, that's just the vector consisting of partial derivatives, the partial derivative with respect to A and the partial derivative with respect to E. And so if we take the partial derivative of this function here with respect to A, what does that mean? That means we keep everything but A constant. So yi minus a sum of yi minus A plus bxi, the whole thing squared. we have to take the derivative of that with respect to a, or just a quadratic function in a, because everything else is considered to be constant. And so we hopefully know how to take the derivative of a quadratic function, and this is what we get if we take the derivative of this with respect to a. If you take the partial derivative with respect to b, we get something a little different because we can see here the videos here, but you can see here that b here is not just b alone, but it's b times x. So when we take the derivative of this with respect to b, we get an x out. So we can see that we get the same thing here, except it's multiplied by xi. So that's the gradient. And now the idea is that we're going to start at some point, and we can choose our favorite point, and then we're going to move from this point towards a minimum. And so the way we're going to do it is we're going to take our point here, and then we're going to the gradient and multiply that by a small number, which is called the learning rate. And then we're going to get a new point, a1 comma b1, and we're going to repeat that. So we're going to take the gradient at the new point, subtract that from a1 comma b1, multiplied by the learning rate, subtract it, and then keep doing that. So I'm going to draw something on the board here that sort of explains why this method here is a good method. So I'm going to shift over to the whiteboard here on my wall, and I'm going to try to make a drawing that hopefully explains a little bit about how this works. So I have my function here of the variables a and b, and I can draw. This is a function of two variables a and b.
Hey, Adam, one question. Sorry to interrupt. I think you may have to stop sharing your screen so that the video